Now we will see the periodic trend of cohesive energy. So by the term cohesive energy, we are referring the periodic trend of melting point and boiling point. Okay. So this is actually a curvy property. Now let's see. So first we have to know that what is a cohesive energy. What is the term means. So you can see there are two different molecules. So the interaction between two different molecules, here blue one and the green one, that is known as adhesion or adhesive energy or adhesive force. Whereas the interaction between two similar type of molecules or atoms, that is known as cohesion. For example, uh, if uh, if you have a group of boys, okay, so if you have a group of boys, so all are boys, so that defines cohesion. And if you have mixture of boy and girl, so that tells adhesion. So cohesive energy or cohesion is related to similar type of molecules or atoms, whereas adhesion is related to different type of molecules or atoms. Okay. Now when there are more than one molecules, they experience intermolecular forces. As we put more than one atoms or one molecules, they will experience some intermolecular force. Either they will attract or they will repulse each other. Now, cohesion is an attraction between molecules or atoms of the same substance. So, as I said, it's a all boys class or all boys property. And adhesion is an attraction between molecules of different chemical substances. For example, as I said, if you put boys and girls together, some boys will talk to the girls, and that is actually adhesion, example of adhesion. Now let's see the definition of cohesive energy. The cohesive energy of a material refers to the energy required to separate constituent atoms or molecules apart from each other, or the amount of energy that is responsible for holding the atoms or molecules together. So here I will try to draw. Let's suppose you have an atom A. Now these atoms are bound to each other. Okay, these atoms are bound to each other by these bonds, and you might think that these bonds are in all four directions. Okay, now if you want to take out one atom from this, you have to supply some amount of energy, and supplying energy you can break these bonds, this one or this one. So you have to supply energy and you have to break all these bonds, then only you can take out this one atom, right? So the energy required to separate this atom from rest of its atoms, that is known as cohesive energy. Or in the other word, you can say the energy that is responsible for holding the atoms. So these atoms, this atom is sitting here, so there is some amount of energy that is making it responsible to sit in that location. Okay, so that also in both terms you can define cohesive energy. Now this is the periodic table which is showing the periodic trend of melting point. And if you see, if you go from left to right, so first the melting point is increasing. So the circle, as big the circle, if the circle is bigger, that tells the melting point is more. And if the circle is small, that tells it the melting point is very low and small, and it easily melts. So as you can see, as we go from left to right, first the melting point increases, the circle becomes more and more big, and then as we go to extreme right, we can see the circle becomes more and more small. So first it increases, then it decreases. Okay. Now same thing you can observe from this 3D bar plot of melting point. You can see this. First it is increasing and getting maxima, and then it is decreasing. So if you follow this line, first it is increasing and then it is decreasing. Similarly, we can see the periodic table containing the information of boiling point of the elements. Now if you see the boiling point, that also refers to the same trend. As we go from left to right, first it is increasing, and then if we go more right, that time it is decreasing. The spots are become more and more small. That means the boiling point is decreasing. Again we will see the 3D plot, and same thing we can see as we are going from left to right. First the curve is increasing and then the curve is decreasing. Okay. Now why it is happening? So we have to understand the factors. What are the factors that are responsible for this type of behavior? So we will see first the trend of cohesive energy along period. Cohesive energy maximizes at group 14, then falls to the minima. So this is the group 14 elements. You can see if you go along period, for example, beryllium, boron, carbon, nitrogen. So the group 14 elements are having higher cohesive energies. And then again it is falling down. For d block elements, yeah, so this one is for the s and p orbital, sp elements. Whereas for the d block elements, it maximizes at group 5, 5 and 6, and then falls. So I will go back, I'll show you again. So see this boiling point data. From here you can see these d block elements are increasing first, cohesive energy, then decreasing, right? Similarly, if you see this S and P block elements, if you consider this SP together, then you will get to see first it is increasing and then it is decreasing. So the maxima is at group 14, means this carbon series. This carbon group, it will show maximum cohesive energy. Whereas in case of um, D, D block element, it shows maximum near group 5 and group 6, this region, somewhere this region. Now what is the reason behind this increased cohesive energy? Okay, that we have to find out. So the availability of number of unpaired electrons determines the extent of cohesive energy. With the increase of number of unpaired electrons, the larger number of bonds can be formed to bring more cohesive energy. Now if you see the electronic configuration, you will see that beryllium is actually 2s2, so completely filled. So I will write here the electronic configurations. Now this one is 2s2, 2p1, and for carbon it will be actually 2s2, 2p2, but so if you see this 2s2, 2p2 will look like this. So first we have this one 2s2 and then 2p2, one electron here, one electron here, and this p orbital is vacant. But what happens during bond formation, hybridization occurs, and this S and P, these orbitals get merged. So this was before hybridization, 2s and 2p. And after hybridization, it becomes 4 orbitals together. And in all 4 orbitals, they have only one electron. So this is called sp3 hybridization. And carbon forms this sp3 hybridization. Now in sp3 hybridization, all orbitals have only one electron. So now all these four orbitals, they can participate in bonding. So this s, 2s and 2p, three orbitals of this 2p, they come together and then they make 4 then sp3 hybridized orbital. These sp3 hybridized orbitals can make 4 bonds. So that is the maximum number. In case of boron, even if you do sp hybridization, that will form only sp2. So only 3 electrons can be there. And if you go to nitrogen, there is one more electron, and that will be here. Even it is sp3 hybridized, that has 5 electrons in total. So 1 electron pair and 3 unpaired electrons. As nitrogen has 3 unpaired electrons, so nitrogen can form at max 3 bonds even after hybridization. Whereas carbon had 4 unpaired electrons, right? See, carbon has these 4 unpaired electrons. That's why carbon can form 4 bonds. So when carbon is in a carbon atoms are there all over, one carbon atom binds to 4 different carbon atoms. Similarly, all other atoms, for example boron, that can bind to at max 3 atoms, nitrogen can bind at max 3 atoms. So this binding increases in case of this group 14 elements. Group 14 because they have 4 unpaired electrons. So if you see again, the availability of number of unpaired electrons determines the extent of cohesive energy. If the number of unpaired electrons are more, the number of bonding will be more. Bonding within same type of atoms. So that's why the extent of cohesive energy will be more. You have to apply more amount of energy to take out that atom, right? Now with the increase in number of unpaired electrons, the larger number of bonds can be formed to bring more cohesive energy. That is what I just explained. Now Ns and Np can accommodate maximum 4 unpaired electrons through sp3 hybridization that I have shown here after sp3 hybridization. So this one is the hybridized orbital, sp3 hybridization. Okay, I'll write this as H, hybridized orbitals, which is attained in group 14. And for d block elements, d electrons can also participate in bonding. As d electrons can also participate in bonding, that's why that d block elements, they have more number of electrons to make this uh, bondings. Okay, so that's why the cohesive energy is also much greater. Now let's see what is the trend along group. So along group, number of available unpaired electrons remains same. So if you go from top to bottom of a group, the shell is same, valence electrons are same. So the number of available unpaired electrons are also same, right? Now for S and P elements, size of the atom increases. So for S and P block elements, if we go from top to down, the size of the atom increases. It becomes bigger because we are increasing the number of shell or orbits. The increased size reduces the number of bonds per unit area. So as the atoms become bigger and bigger, the number of bonds per unit area decreases. So if you have this, just see, if you have this carbon atom, let's suppose, so it can bind with this atom, it can bind with this atom, and it can bind with this atom, it can bind with another atom. Now see, within this much area there are so many bonds. So you can just multiple it. All these atoms are bound with four other elements. Now if you see silicon or let's say tin, the atom size is bigger. Now that is bound to another bigger atom, that is bound to another bigger atom, now another bigger atom, and another bigger atom. Similarly, these atoms are also bound in all four direction. But here the circle is much bigger compared to this, right? So we have same number of unpaired electrons, we have same number of bonds, but the as the atom size is small, here we have more number of bonds per unit area, whereas as the atom size is bigger, here we have less number of bonds per unit area. So hence the cohesive energy decreases in S and P block elements as we go from top to bottom because the size of the atom increases. Now for D block elements, size change is significantly less due to the D and F contraction, which I have already explained in the previous lecture. So because these D and F electrons are diffused, they have less shielding power, and that's why the nucleus have more attraction towards the outermost valence electrons. So that's why the size change is significantly less. As we put more and more protons, it can attract the outermost electrons, and size is almost similar. So density of atoms increases. So the density of the atom also gets increased, and these heavier elements experience higher cohesive energy. So if you see here, as we go from top to bottom of a group in S and P block element, we can see the cohesive energy actually decreasing. For carbon, it is maximum, then silicon, germanium, tin, lead, the cohesive energy amount is decreasing. Whereas if you see in case of D block element, so in D block element, this curve is for the 3D element, 3D elements. Now if we go down, this one will be for 4D elements, and this one is for 5D elements. So this one is chromium, molybdenum, and tungsten. So this one chromium, then if you go down molybdenum, and if you go down tungsten. So along the group we are going down, but these heavy, as the atoms are becoming more heavy due to D and F contraction, the cohesive energy is increasing. So here you have to remember that cohesive energy for S and P block and D block along group runs in the opposite direction. Okay. Here you can see the atomic number versus melting point graph. This one, and on the right hand side, the same graph you can see. So the scale is different. It is in Kelvin scale, and this one is degree centigrade scale. So here, from here we can see that carbon is having the highest melting point. And here in these plots I am showing you the atomic number versus boiling point data. So here boiling point is given in Kelvin scale, and these ones are the data. You can see, if you need for your reference, you can take a look of this periodic table. So let's discuss about the key points. So we have observed that this trend in cohesive energy is actually a curvy property. So first it increases, then becomes maximum at group 14 in case of S and P elements, and in group 5 or 6 in case of D block elements, and then it comes down. So the cohesive energy of a material refers to the energy required to separate constituent atoms or molecules apart from each other. The availability of number of unpaired electrons determines the extent of cohesive energy, and with the increase in number of unpaired electrons, the larger number of bonds can be formed to bring more cohesive energy. Now along period, cohesive energy maximizes at group 14, then falls to the minima. And for d block elements, it maximizes at group 5 and 6, and then it falls. Inert gases having only weaker van der Waals force acting as the intermolecular interaction have the lowest cohesive energies. And along group, cohesive energy decreases in S and P block elements if we go from top to down, whereas it increases in the case of D block elements due to D and F contraction. Okay.
Hey genius, I hope you liked the video and the concepts are clear. So if you want to know more and if you want to learn more, you can go and check the periodic table and periodic trends folder. I have already uploaded 7 lectures on this topic. Please go and watch all those 7 lectures. I hope it will be very useful for you. And if you think these videos are knowledgeable, please share it with your friends and don't forget to subscribe. Okay? Thank you. Bye bye.